let's get started. So, welcome to this talk on unintended memorization and timing attacks in named entity recognition models. This was work done with my group over in Macquarie University in Sydney, Australia. And let's jump straight into it. So, what exactly are named entity recognition models? These are essentially language models trained to label entities within text. You train it, tell it, teach it how to recognize a particular entity, whether that's, in this case, if I have a sentence, Benjamin is presenting work at PETS, it will name entities with it that you've taught it. So in this case, person is labeled as an entity, the date, as well as various organizations. And the flexibility with machine learning is once you've taught it to recognize these entities is you can give it any large amount of text and it will go through each and every single one of these words, phrases, and also label those learned entities. So these language models, these named, or these NERs, as I'll call them from here, they, in themselves, are not particularly privately vulnerable. But if we apply them in a setting such as text redaction, we introduce a much larger risk profile. And text redaction, in a typical sense, its objective is to remove sensitive or private information from documents. And very typically, this has been a manual process. You take, say, a physical black highlighter, you black out any sensitive information. Or you could have an electronic black highlighter and you still redact that same sensitive information. Now, this physical process is quite laborious, especially if you have thousands of documents. So there have been processes to sort of speed this up, automated processes. Now, one way of doing that currently is using predefined rules. But unless you know how every single possible piece of sensitive information will present itself within your documents, it may miss pieces of sensitive information. And it's quite inflexible to these new formats. And that's where these NER machine learning models have an appeal for text redaction. Specifically, in our experiments, we'll look at the spaCy library, a very widely used language model library in Python. So that's our motivation here. We have our NER models, we have text redaction, a sensitive application. So what we're going to talk about for the rest of the talk is we'll go through how exactly we launch membership inference attacks. And with membership, you can leak that private information from the training data set of your NER. And in text redaction, that's the specific sensitive terms that you were trying to hide in the first place. We'll look at the assumptions we have for this attacker, and we'll look at two different ways of actually achieving membership information through the traditional memorization within machine learning, but also this novel new timing side channel. After I sort of set up the attack, we'll look at a brief set of results about characterizing the memorization. We'll look at a use case with medical documents, and we'll also look at our attack timing service and go through some defenses through the process. So let's begin. In our training data set, if we have that same sentence as before, there will be a sensitive term within it, and that's what will be redacted in the end. However, surrounding that sensitive term, you have the remainder of the sentence, or as I shall call, the surrounding sentence. This is typically the insensitive part and may be held by that company. So with that established, our attacker, we assume, has access to three key things. They will have access to that text redaction NER model. That may be achieved either through, say, the company wanting to monetize their text redaction model, giving paid public API access, or if you have an internal attacker with access to that model. We assume that the company, well, the attacker has access to this surrounding sentence, either through redacted document release, through freedom of information requests, court proceedings, or data sharing. That surrounding sentence is available. And we also assume that the attacker is able to curate some list of potential redacted sensitive terms, whether that's persons of interest or from larger dictionaries in which the sensitive term may exist. For example, if we consider passwords, that could be rainbow tables. Now, with access to the surrounding sentence and these potential redacted terms, our attacker can construct multiple different sentences that potentially contains that training sensitive information. And with each of these potential sentences, we will feed them into the NER model, and the NER model does as it was trained to do. It will label the entities within those sentences. In this case, person, date, organization. So where the membership inference attack comes in, if we're considering memorization, these entities will be labeled not just with an output class, but with a confidence. And following traditional membership inference through confidence attacks, the more confident a machine is in a particular output, the more likely it is to be part of that initial training data. And if it's below a different threshold, it's probably not in the member data. The alternative approach is through timing. Now, with these language models, if we feed both of those sentences in, those models will actually output a response, its classification, a bit faster when it has previously seen these samples in training. And based on the speed of that returned output, you can figure out if it was a member or a non-member, thereby leaking information about the training data set. Okay, so that's how the attacks can be launched. Now I'm going to bring us into a little study of characterizing memorization. And for this characterization, we look at how well these NERs memorize passwords. I'm not going to go through the full set of results here. I'll sort of refer you to the paper for more details. But the sort of things we look at when characterizing this behavior is the number of insertions. It doesn't matter if the sensitive information was present in the data set, training data set, 3 times or once. Once is more than enough for that model to memorize the sensitive term. If as we're dealing with passwords here, we also look at potentially if there is more complex passwords, will that model memorize more eagerly? For example, entropy of that actual term. We also look at 2 additional behaviors of the model. If we didn't have access to that entire password, what if we just find every possible permutation, feed every single one of them into the model? We look at the output confidence and how easily an attacker could actually get to that exact word or password. And we also look at multiple different types of sensitive private information, things like credit card numbers, phone numbers, and IP addresses within that NER model. So I've been very brief about this, but if you want more details, please refer to the paper. It characterizes how the NER models behave. So in the next little section, I'll talk about a specific application of text redaction with these NER models, where we train a model, or NER model, on medical records. After that, we have that assumption of the surrounding sentence. What if the attacker didn't have access to that? We'll look at the timing surface and, again, more defenses as we go. So this medical data setting, we have a corpus of digitized doctor-patient reports. And within them, there are sensitive private information of the individuals, things like names, addresses, contact details, patient ID numbers. And with this corpus, we sort of split it into our member and non-member data sets. We train with the member, we keep the non-member for testing. And we find that these NER models are vulnerable to membership inference. We are able to infer whether those specific patient information is contained within the training data set. An additional property that we observe during this process is, during the training of the NER model, if the number of representative samples for your entity, in this case, contact details, if you have less samples available for training, the model will sort of capture more information from those limited number of training samples, thereby memorizing them much more and leading to a more successful membership inference attack. Now, that was for medical data, but we also show that this behavior persists with passwords or secrets. This NER model is equally vulnerable for that type of data in addition to the medical patient data. Yeah, so we've established that membership inference, the attack works. Now, one of those assumptions was access to the surrounding sentence. What if we take that away from the attacker? What if the model was trained with a series of sentences, and then we test with a wholly different sentence? We see that this membership inference attack, it collapses. And essentially that attacker, that membership inference attacker, needs that surrounding sentence to perform well. You might think, oh, let's defend against it by removing the sensitive data during training. So in this example, we take a sentence with location information and we substitute that location information with fake or other location information. We show that the membership inference attack goes down to a random guess, but this comes at an expensive cost in our utility of said model. It goes from about 0.8 F1 score down to 0.2. So the sort of conclusion from that is you need to be quite careful in how you select these data substitutions if you were to replace that sensitive information. So let's move to the timing attack. So same as before, we have a sentence coming into the large mechanism that is the language model, and we have an output. So the intuition is the spacey architecture. It manages a cache of vocabulary to speed up repeated queries. And in our setting, we look at multiple different tokenizer architectures as well. Pretty much, there is a very visible timing difference between members and non-members, and the attack, membership inference attack here, is very successful. And if we look at the timing distributions, we can see how it's very clear we can separate those two classes. Now, initially our intuition was that vocabulary, once it gets updated, this timing information should go away. But even after multiple subsequent runs, we can still successfully perform a membership inference attack, despite the updated vocabulary. So there are still other internal mechanisms that is leaking private or this timing information or membership information. Our defense is quite straightforward. We add a little fixed delay, make the members look like the non-members. And with that, the membership inference vulnerability goes away. So to sort of finalize, the key takeaways here in our talk, we've shown that these NER systems are vulnerable to memorization, which leads to membership inference. It's important for the attacker to possess the surrounding sentence. And when you're sort of replacing the sensitive data with dummy words, that comes at a cost to the utility of the actual model. We saw that these inference speedups created a new timing attack surface. And I will remark that if you are creating defenses for this private information, if you're using conditional logic for member and non-member information, you may expose this information as well. But ultimately, there remains work to be done in order to create these private NER models. But that's the end of the talk. If there are any questions, feel free to ask.
Thank you. So you presented some kind of not working defenses or offenses that can the next person start? Or the defenses that have some sort of drawback in them?
Yes.
Do you have any ideas of how to actually create a good defense for this? Do you use large language models to generate text that you can then label, or?
We didn't look at sort of creating a working defense on the memorization side of things, just because there are so many possible defenses available. For example, like differential privacy, but most of them do still come with that utility cost.
Right.
And that will be an entire research project in itself.
Do you have an idea of why it really takes a big utility hit? Because it just seems that it doesn't seem so intuitive that it should take a utility hit just by like maybe switching the different types of secret information or sensitive information.
I think like I mentioned during the talk, it comes down to being able to sort of match a distribution that would come in through the unseen data. So even if your language model thinks that this is the distribution that has been captured in the training data, whether that actually reflects what's incoming, how we verify that, that's the difficult part.
Okay, cool. And I think that we don't have any questions on Zulip for this very early morning session. So with that, we'll thank our speaker again.